Okay, so I wanted to work through some of these sample calculations that you'll need to include in your lab report. And I need you guys to take some time and look at these and understand what we're doing here. Okay, so we're not trying to introduce a whole super new concept. That's not the point. I'm not going to test you separately on this. But I do want you to look at your lab and understand what these calculations mean, even though some of these things are right on the edge of what you guys can understand. All right, so I'm going to just work through this really fast. You have all this in your lab report. So if you don't have that lab report in front of you, pause this video and get it out. Okay? All right. All right. Man, I don't know why I'm having such trouble with this thing focusing. And you get it some Ritalin. It's having some ADD issues with focus. It's still not wanting to focus. Let me give it something to focus on here. All right. So you've got this equation right here, and you've also got this equation. Molality is equal to the number of moles of solute per 1 kilogram of solution. Okay? All right, well, we don't have 1 kilogram of solution, so that's the first thing I want us to focus on, because this M is what comes in right here. Okay? All right, so what do we have? You guys have 100 milliliters, which equals 0.1 liter, which equals 0.1 kilograms of H2O, okay, or of solution, okay? And I think as you add, since it's 1 kilogram of solution, is it solution or is it a solvent? Hold on 1 second, let me flip over and check that. Okay, it's per solvent, which is good because that helps us, because the solution changes as we add mass into it. All right, so 0.1, we have 100 milliliters, so we got 0.1 kilogram of H2O, which is our solvent. All right, so our molality at the end of the day cashes out to some number of moles of your solute that we dissolved in there per 0.1 kilogram of solvent. Okay, so we're going to take that, we're going to plug that in over here. All right, so what's that going to give us? All right, so you guys, and Ann Mabry sent out her number, so we're just going to take her number and we're going to go with that one, okay? So our normal boiling point's 100, hers is 105, and so our change is 5 degrees C. Okay, just subtract the 2. You can show me that. Okay? I'm going to actually make this camera come down a little bit closer here to get you guys a little bit better of a view of what I'm doing. Okay. All right, so what's our KB and where does it come from? Where I tell you it's in page 282 of your book, and for us it's 0.513, and that's for the water, and we're using water for all of our things, so that's the only one number we ever need to use there. So it's one less number you got to worry about. Okay, times this M, so we're just going to put the number of moles of solute per 0.1 kilogram. Okay, just in for that. We're not going to try and solve for anything yet. All right, now this is a little bit tricky, and I kind of realize that I'm giving you 2 unknowns here. Let's assume that, all right, so this I is how many ions does that thing break into when you dissolve it? Okay, let's just assume we've just got 2. Okay, so sodium chloride, a common salt, for example, breaks into Na plus and Cl minus, which we're going to get really into this coming week. All right, so that makes 2. 1 mole goes in and 2 moles are what it breaks into. Okay, so we're just going to do that. All right, and now we're going to move these over here. So we'll have 5 divided by this 0.513 times 0.1 divided by 2. So our number of moles of solute is then going to be equal to what? What is that number that we've got here? That's going to be 1.25 moles. Okay? Nope, that's not right. Sorry. That's not the right answer there. Okay? That's going to become 0.487 moles. Sorry. All right, so 0.487 moles, and obviously these numbers will be different for whatever you do, but follow these same steps and plug in your numbers and see what you get. All right, so number of moles of solute, 0.487. All right, well, how many grams of solute did you add? You were told to add 25. Okay, so now maybe you got 24.9, or maybe you got 25.1. It should have been pretty close to that, but we're just going to assume that our grams of solute is equal to 25 grams, where you hit it right on the money. Good job. Okay, how do we get there? So we have 25 grams of a solute. All right, now normally we'd say 1 mole per some number of grams is going to give us our total grams. Let's see. Oh, that's going to give us our total number of moles, 0.487 moles. Okay, so what do we have? We have 25 over x is equal to 0.487 moles. And we multiply both sides by x, divide by 0.487, so we end up with 25 over 0.487. You don't have to show me this step, but you need to get me to maybe something like this, okay? Equals x, and so then x equals 51.33 grams per mole as a molar weight. All right, so now we need to look at our common salts, okay, which are going to be one of these guys mixed with one of these guys, or paired with one of these guys. Okay, so one of our alkali metals, or alkali metals over here, paired with one of our non-metals over here. In this case, they happen to all be halogens, okay, because they break apart really easily into ionic species, okay? All right, and so we look at those, and we say, all right, what are some of those, and what are their whatever. I'm probably just going to send you guys an email and telling you what your solutes were, and just so, because it's too much unknowns for you guys, and I kind of overestimated, y'all's familiarity with that, and that's entirely my fault. That's nothing y'all are failing at. That's my fault. All right, so in this case, our solvent 1 was NaCl. Okay, I know that because I told y'all it was. All right, so what is this one? That's 23.0. We can round that one. Grams per mole. And Cl is 35.45 grams per mole. So we add those together and we end up with 58.45 grams per mole. All right, so now we can go about our percent error calculation 2 ways. Okay. All right, so we can compare anticipated molar mass to calculated molar mass. Okay, and I'll show you how to do that in just a second. Or we could plug this in to this equation and calculate what our change in temperature should have been, and then we look at what our change in temperature actually was, and we could work that out. And I think they should be the same percent error because they're all using the same numbers. Okay, so let's look at that really fast. Okay. All right, and I just looked that up and I was reminded that he calls it percent difference, not percent error, but that's a small little quibble there. All right, so let's plug in some of these numbers so you guys can see how it works. Okay, so what do we have? Let's say our percent difference is what we're solving for. All right, so what was our predicted? We'll call this our predicted. 58.45 grams per mole minus what was our experimental here. Why does he call that accept? Sorry, this is actually experimental here. Copied it wrong. All right, so what's our experimental? Well, what we calculated after we did our experiment was 51.33 grams per mole over the predicted. Okay, and so what does that equal at the end of the day here? We got 58.45 minus 51.33. All right, and then we're going to divide that by 58.45. All right, so that's 0.122, and then times 100 is equal to 12.2% difference. Okay? And you can work that exact same one with the temperatures if you'd like. I'm pretty sure, like I said, I think it's going to come out to be the same regardless. I think you're going to get 12.2. You work it the other way. Y'all are welcome to just copy this, or you're welcome to do it the other way and report to me whether it's different or not. Obviously, each one of your experimental errors are going to be a little bit different because you have different temperatures that you were measuring and different reasons that they could have been a little bit inaccurate. Okay, so real quickly, I will tell you that I want you to go ahead and I want you to work these. Well, what I want you to do, I want you to work it like this, like it's an unknown solute, okay? And then I want you to compare it to solute number 1 was NaCl. Number 2 was, I don't remember what order we put them in. Number 2 was calcium chloride. Okay, and we'll talk about why that's a CaCl2. Okay, we'll talk about that actually well, probably not Thursday because we're a little bit behind, but soon. Don't worry. I know you guys are champing at the bit to get that ready. All right. Number 3 was potassium chloride. Okay. So this one breaks into I equals 2. Guess what? Ca2 plus, Cl minus, Cl minus. I equals 3 for this guy. And then I equals 2 like we just saw right here for him. Okay? All right, so now use this knowledge after you've done this, okay, to go through this right here. Okay? And I think this is what Ms. Barron was trying to get you to do, and it's just too much if you don't know these, okay? If y'all had super awesome thermometers that let you zoom right in on an exact temperature, you could solve for a molar weight, and it would probably be like 57.9 or something like that, and you could probably figure out, oh, NaCl, all right, because it's 58.45. You guys just don't know about salts yet, though, and which ones are common, and your temperature was not, so you got a lot of unknowns, so I'm sorry about that. So this is the information right here that you need to know. All right, and if you got any questions, I will try to get those answered really quickly so that you guys can get your lab reports written. All right, thanks. Bye.